Limiting reactant problems are a good application of stoichiometry. So if you know how to do these type of problems, you really have mastered the art of stoichiometry, which is going to be important in all of chemistry and in advanced chemistry courses as well. So I thought I'd go over two practice problems that utilize this concept of limiting reactant. The concept is very simple. You have your reactants here, and one reactant is going to limit the amount of product that is going to be formed. So either this reactant runs out first, or this reactant runs out first. If this reactant runs out first, it is limiting and sets a limit of how much product you can make, whether it's this C3H3N solid, whether it's this water as the product, or whether it's this nitrogen gas as the product. If this C3H6 gas is limiting, that means all of it as a reactant gets used up first, and that sets a limit of how much this C3H3N sulfur solid product is formed, as well as sets a limit as how much of this water is formed, as well as a limit of how much of this nitrogen gas is formed. So the limiting reactant is a reactant. It's not a product, but it is actually a reactant that limits or sets the criteria for how much product you're going to form. Obviously, if one reactant is limiting, that makes the other reactant excess. And the excess reactant is something that's going to be left over when the reaction completes its course. Can be made from 21.6 grams of C3H6 and 21.6 grams of nitric oxide. First thing you want to do is check to make sure you have a balanced chemical equation. So check if the equation is balanced, and we can see here that it is balanced. So check for a balanced equation. After you have checked for the balanced equation, then you can go ahead and determine which is the limiting reactant. Now, is this the limiting reactant? If that's the case, then this is an excess. Or this can be the limiting reactant, and if that's the case, this is going to be an excess. Your limiting reactant is always going to be the reactant. Remember, reactants go to products by basis of the stoichiometric coefficients. And what is our starting material? We start off with 21.6 grams of C3H6 and 21.6 grams of nitric oxide. So is it safe to assume that all of this will react with all of this? Because after all, we started off with 21.6 grams of propylene and 21.6 grams of nitric oxide. All of this will react with all of that. We want to figure out how much of this we make. That is a wrong approach. That is completely wrong, because we have to use stoichiometry to determine really how much of this can actually get made. So we still have to calculate what is our limiting reagent. It's either going to be this one or that one, and the determination of what is the identity of that limiting reactant is based on stoichiometry. So we have to calculate how much C3H3N, this acrylonitrile, is made if all of this is used up, and how much of this acrylonitrile is made if all of this is used up. So we have scenario 1 and scenario 2. So our first scenario is to calculate how much of this acrylonitrile product is made when all of the propylene gas is made up. So we started off with 21.6 grams of this C3H6 as our starting material. And now let's use stoichiometry to determine how much of this product you will make if all of this reactant is used up. So we start off with 21.6 grams of C3H6. And a good thing to do is actually just go ahead and convert it to moles. That's what you can do 99.9% of the time when you're dealing with this problem. Not always, but in this case, to approach this problem, we will start off with 1 mole of C3H6. And for every 1 mole of C3H6, we have a molecular weight of C3H6. So 1 mole of C3H6 contains 42.01 grams. Now times, this is one of our definitions of the mole. Our second definition of a mole is that it's the coefficient of our balanced chemical equation. So let's go back to our balanced chemical equation here. We know that for every 4 moles of C3H6, there's 4 moles of C3H3N, because this equation is balanced. So for every 4 moles of C3H6, we have 4 moles of C3H3N. That is basically from our balanced chemical equation. And we can actually stop here and figure out how many moles are produced from this many grams. But let's just go ahead and convert this to grams. Now you can stop right here. That's perfectly all right. But I'll just go ahead and convert it to grams. All right. So 1 mole of C3H3N has how many grams of C3H3N? I have roughly 53.01 grams of C3H3N in 1 mole of C3H3N. So here's where the magic of stoichiometry comes in. The grams of C3H6, the grams of C3H6 cancels with the grams of C3H6. The moles of C3H6 cancels out with the moles of C3H6. And I could stop right here to get the moles of C3H3N, but like I said before, I'm going to go with grams. So the moles of C3H3N, this acrylonitrile, cancels out with the moles of C3H3N. And ultimately, I will get the grams of C3H3N from my starting material of C3H6. 3 sig figs, 27.3 grams of C3H3N. This means if I use up all of the reactant C3H6 propylene gas, I will produce 27.3 grams of this arsenonitrile or acrylonitrile substance, this solid. Now we're testing our second reactant. We start off with, according to the problem, 21.6 grams of nitric oxide. 1.6 grams of nitric oxide, and let's just go ahead and convert it to moles. 1 mole of nitric oxide will have how many grams? 30.01 grams of NO. And we know that, go to our balanced chemical equation here, we know that for every 6 moles of NO, I have 4 moles of C3H3N. Okay, so for every 6 moles of NO, I have 4 moles of C3H3N. I generate that from the balanced chemical equation that was given to me. For every 6 moles of NO, there is 4 moles of C3H3N. I could stop right here. But I'll just go ahead and convert this to grams. So now I will take 21.6 grams of NO, multiply it by 4, multiply that by 53.01 grams, and divide that product by parentheses 30.01 times 6, close parentheses. And that will give me how much grams of C3H3N I produce if I use up all of the 21.6 starting material of nitric oxide. I did this calculation. I got 25.4, I'll put another sig fig there, 25.43 grams, or I will just put it to 3 sig figs like this, 25.4 grams of C3H3N. So what does this mean? It means if I use up all my reactant NO, I will produce 25.4 grams of C3H3N. So utilizing stoichiometry, if I use up all of the starting material of NO, I will produce 25.4 grams of C3H3N. Let's compare that to what we get if we use up all of our other reactant, which is C3H6. So if we use up all of C3H6, the propylene gas, if we use up all of the propylene gas, this C3H6, we wind up with 27.3 grams that is produced. So let's do a comparison. If we use up all of this reactant, we make this much product. Use up all of this reactant, we can make this much product, potentially. If we use up all of this reactant, we can make potentially this much product. So using up all of NO as the reactant, we produce 25.4 grams of product C3H3N. And using up C3H6 propylene gas, we actually can make 27.3 grams of our C3H3N acrylonitrile product. So what sets the limit on how much product that is produced? It's going to be this one. So our limiting reagent is actually nitric oxide. This would be our excess reagent, which is C3H6. excess reagent. This, as we found out, was our limiting reagent. We used stoichiometry. 25.4 grams of this can be made. Made from utilizing all of the 21.6 grams of nitric oxide. Some of this stuff, the 21.6 grams of ethylene, the 21.6 grams of propylene gas is going to be left as excess. Since this is the limiting reactant, it actually limits how much this is produced, how much this is produced, how much this is produced, and how much this remains. So we actually can calculate the excess reagent based upon the fact that this gets all eaten up to make this, and this gets all eaten up to make that, and this gets all eaten up to make this. This gets all eaten up first. This is left over. How much of this is left over? Problem even more, we can state that we start off with 21.6 grams of NO as our limiting reagent. That sets the limit on all that is made and all that can react. And we know that for every 1 mole of NO, we have 30.0 grams of NO. And we, based on the balanced chemical equation that we see, the balanced chemical equation, we know that for every 6 moles of NO, there's 4 moles of C3H6. 6 moles of NO, there's 4 moles of C3H6. I could stop here and just figure out how many moles are produced that is in excess, but I'll just go ahead and convert this to grams. For every 1 mole of C3H. So utilizing this calculation, the grams of NO cancels with the grams of NO. The moles of NO cancels out with the moles of NO. The moles of C3H6 cancel out with the moles of C3H6. So when all of this NO is used up, that means this NO as the limiting reagent will react with 30.16 grams of C3H6. Produce, we already figured out how much product it's going to produce from our stoichiometry. So this implies that our excess reagent, C3H6, you started off with 21.6 grams. Limiting reagent eats up 20.16 grams. So how much excess of C3H6 propylene gas that's left over is going to be 21.60 minus 20.16. Look at problem number 2. When iron 2 hydroxide is mixed with phosphoric acid, iron 2 phosphate precipitate results. So here's our balanced chemical equation. Iron 2 hydroxide plus phosphoric acid yields iron 2 phosphate plus water. So they're telling us that if you have 3.20 grams of iron hydroxide and it's reacting with, remember, always put a unit by your number. It's reacting with 2.50 grams of this phosphoric acid, aqueous, which means it's dissolved in water. This aqueous also means it's dissolved in water. The solid means it's a solid. What is the limiting reagent and what is the reactant in excess? So whatever you identify, the reactant is limiting, the other one is going to be in excess. How much precipitate is made? The solid precipitate, well, that's determined by the limiting reagent. And then if you actually get 3.99 grams of iron 2 phosphate, what is the percent yield? Remember, the percent yield is, because it's a percentage, we multiply it by 100 to get it into a percent. Ask yourself the question, is this the actual yield, this number, or is it the theoretical yield? This is actually the actual yield. Theoretical yield is what you get based on your calculations, based on your stoichiometry, based on canceling out units. This is what you actually get when you do the reaction, filter it, put on gloves, weigh the material, do the actual messy lab work. Once we balance the chemical equation, we're ready to determine the limiting reagent, and then we're able to successfully complete A, B, C, and D of this problem. My balanced chemical equation is 3 iron 2 hydroxide plus 2 phosphoric acid goes to iron 2 phosphate plus 6 H2O. First thing is to figure out which is our limiting reagent. So let's assume one of these is going to limit the amount of product. We started off with 3.20 grams iron hydroxide and 2.50 grams of phosphoric acid. let's assume all of this is used up. So we start off with 3.20 grams of, and according to the balanced chemical equation that we just balanced, from the balanced chemical equation, for every 3 moles of iron hydroxide, 1 mole of Fe3PO4 product. I'm just going to stop at moles here. I will not convert it to grams. Here at moles, and I will not convert it to grams. I'll just go ahead and figure out how many moles are produced from 3.20 grams of iron 2 hydroxide. Now we want to figure out how much of our iron 2 phosphate is produced if all of this is used up. So we'll do our stoichiometric calculation again. This time we're starting out with 2.50 grams of phosphoric acid. But for every 1 mole of phosphoric acid are in 1 mole of phosphoric acid. And we know, based on our balanced chemical equation, that for every 2 moles of phosphoric acid, there's 1 mole of iron 2 phosphate. Iron 2 phosphate. So the grams cancel, the moles of phosphoric acid cancel. We're left with moles of iron 2 phosphate. I'll stop at moles. Now, which is the limiting reagent? Is it going to be the phosphoric acid, which sets the limit on how much iron 2 phosphate product is formed, or is it going to be the iron 2 oxide, which sets the limit on how much iron 2 phosphate is formed? Well, you're only going to produce 0.0127 moles of this from this. Here you can produce 0.0109 moles of product from this, so this is obviously the limiting reagent. And let's figure out our theoretical yield, how much we get. So that is actually how much we can best produce. It's perfect. We actually got 3.99 grams produced. 9 grams produced. Actually, theoretically produces 4.55 grams based on the limiting reagent of phosphoric acid. So our yield is 3.99 grams. Our theoretical yield based on stoichiometry is 4.55 grams. We'll divide it by theoretical. Let's determine how well we were able in capturing this iron 2 phosphate precipitate. Action is 87.7% efficient. In our limiting reagent, determining which one is our excess, and then from that excess and from that limiting, we were able to determine how much of this yield we were able to capture. We were able to capture about 88% out of the 4.55 grams we could produce based on stoichiometry.